All right, now let's take a look at some examples. To apply pigeonhole principle, the key is to cleverly construct pigeons and holes. Otherwise, it can be challenging. Okay. Well, certainly don't get frustrated at the beginning because it does take some exercises to know how to pick your pigeon, how to pick holes. So let's begin. Say there are 7 students in a class. Must there be at least 2 students who were born in the same month? So now you think about here. There are 7 students, right? 7 students, 1, 2 to 7. Let's label 1 to 7, and there are 12 months. 12 months. And probably without using pigeonhole, you can quickly answer, nope, not necessarily. These students can be very different. They were born in different months. That can happen. From the pigeonhole's perspective, you have 7 pigeons where n is equal to 7, and you have 12 holes. M is 12 because this is not greater than that. So therefore, not necessarily that at least 2 pigeons will be in one hole. So because this is not greater than that, so that might not be the case, right? So no, answer is no because n is not greater than m in this case. Now what about this? In another class, there were 25 students, and must there be let's begin with that. Suppose there were 25 students in a class. Must there be at least 2 students who were born in the same month? So in this case, we are going to say yes. So in this case, your pigeons will be these 25 students, right? So student number 1, student number 25, okay? So there were 25 students. And the holes will be the month, like January, February, and to December. And the function f, the mapping f, will be f of the ith student is equal to the birth month, right? The birth month. So in this case, you can see that n is equal to 25 and m is equal to 12 because n is greater than m. Therefore, by the pigeonhole's theorem, principle, that there must be at least 2 students who were born in a. So there must be at least 2, right? At least 2 students share the same birth month, sharing the same birth month. So we can conclude that. Now, what if the question becomes, must there be at least 3 students who were born in the same month? Now let's check. So for the second part, must there at least 3? So this is part 1. Part 2, then we use n divided by m and take the Serling function, right? So therefore we have 25 divided by 12 and take the Serling function, which is like 2 point something, right? 2 point something. And then you run to the next integer, which is 3. So must there be at least 3 students who were born in the same month? Then yes, we can conclude that it's yes. So this is the first example. Let's take a look at the next example. So again, you have to find a way to define your pigeons and define your holes. The second example is, must there be at least 2 people in the New York City? So New York City, it's about a little more than 8 million, less than 9 million at the moment, with the same number of hairs on their heads. So, according to the scientific research, the maximum number of hairs in a human being is less than 300,000. So, let's see. Now, what would be your hole? What would be your pigeons, right? So, think about that. You can feel free to pause the video and think about that. So, the pigeons will be your 8 million people. So, 8 million people. And the holes will be, you number of hairs, right? Some people may have just 1 hair, 2 hair, and 3 and 300,000. So there are 300,000 holes, and these people are sent to by the number of hairs. If some, by the way, maybe some zero hair. Some bald people, then they are mapped to 0. If just 1 hair, it's just mapped to 1, and so on and so forth, right? Now, N is 8 million, okay? And then your M, the holes, will be 300,000 K, which is 0.3 million, right? 0.3 million. So because M is greater than, N is greater than M, I'm sorry, the other way around. Therefore, answer is yes. There must be at least 2 people in New York that share the same number of hairs on their head. Now, actually, at least how many people will have the same number of hairs? So then we will use, so for the second part, we use N over M and then take the scaling function. So we have 8 million and then 0.3, right? Okay. So if you do this algebra, this is actually about, so this is like 26 point something, okay? So therefore you can run to the next integer, which is 27. So at least 27 people have the same number of hairs on their head. Well, this is the second example. Let's take a look at the next one. Must there be at least 2 students in a class with 13 students who have the same birthday? Okay, so same birthday. So the birthday, how many different birthdays are there? I think there are 366, right? Including in case there's a leap year. And now those are the holes, and I have 13 pigeons that we send to those birthday, which is the holes. So here, this is the pigeon. Pigeon will be our students, like in this case 13 students. And F is the mapping that send them to the holes, which is the 366 different birthdays, different days. So F of student, ith student is equal to their birthday. So in this case, N is 13, M is 366, right? So because N less than M, therefore not necessarily that we will have 2 students share the same birthday. So not necessarily. What about on campus, like the whole campus? Okay. So for sure we have more than 366 students, right? Because we have that the N in this case is more than 366. In that case, for sure, that's yes, right? Because use common sense, N is more than 366, which is the M. So, okay. Now let's look at the last question of the last part of the first question. Let's say suppose we have 9 students in this group math class, and there are 5 possible grades, A to F, A, B, C, D, F. Does it guarantee that at least 2 students have the same grade? And if so, at least how many students will have the same grade? So think about what would you use for pigeon and what would you use for holes. In this case, the pigeons will be the 9 students. 9 students. And the holes will be those A, B, C, D, F, those 5-letter grade, right? So the mapping is F of student I is equal to his or her grade. So it's his or her grade. In this case, N is 9, M is 5. Now, to answer the question, for sure, there were at least 2 students that share the same grade because this is greater than that. Now, if you even look at N divided by M, 9 over 5, and then take a scaling function, this is going to be 1.4, right? 1.8, I'm sorry, 1.8. 1.8. So which is actually equal to 2, the scaling function. So at least 2 students, that's what we guarantee. We cannot guarantee more than that. So it could be more than that, but that's what we guarantee. So that's this last example. Now let's take a look at a fun one. So let's take a look at this. Would be a good puzzle for students to solve. Say JD wakes up in the morning and finds that he has only 5 minutes to rush to his morning class, and he has 10 white and 10 black socks in his drawer. He needs a pair of socks, but he doesn't have time to even look at the color. What is the least number of socks he must grab to be sure he gets a matched pair for the class? Okay, so now let's think about what would you call pigeon and what would you call holes, right? So pause the video, think about it, and here it goes. So pigeons, if you think of those socks as pigeons, so there were 10 white, 10 black. So 10 black. So there are 20 here. And the holes, so think about the color. One is white, one is black. And the mapping, the F. So F of, so the socks. The sock grabbed is equal to the color. So that's the way it is mapped. Now, because the whole is how M is equal to 2, right? M is equal to 2. You want to have at least, say, 2, each hole has at least 2 pigeons. Then you want this to be like 3 or more, right? So therefore, because M is equal to 2, number of holes is equal to 2, therefore your N, which is the number of pigeons, must be greater than or equal to 3. So therefore, he just needs to grab 3 socks. Then that guarantee he gets a matching pair. So therefore, 3 socks, right? That's how many he should grab. Now, what if he has 10 white, 10 red, 10 blue, and 10 yellow socks? So in this case, again, please pause the video and think about what would be your answer this time. So again, you have 10 white, 10 red, 10 blue, and 10 yellow. Okay, and the holes will be white, red, blue, and yellow. So the M is equal to 4 because N is equal to 4. Therefore, N, which has to be more than 4, right? So greater than or equal to 5. So therefore, 5 socks has to be grabbed to guarantee a matched color. All right, I'm gonna stop the video here, and we'll look at actually how about we we'll look at the other problems in a separate video.